Hi, this is welcome to the 9 live session on the Points Topology NPTEL Part 2 course. My name is Shavik and I am currently doing research on doctoral counseling matrix. So before starting, please let me know whether I'm audible and is the screen visible to you. Please let me know. Okay, thank you. Hi, Mr. Can you confirm whether am I audible properly now? Hi, Mr. Can you confirm whether am I audible properly?
Yes, it's audible.
Okay, thank you for confirmation. Sorry for that inconvenience. Okay, so before starting further, please let me know, do you have any question or any doubt? Before starting further, please let me know, do you have any question or any doubt?
No, no.
Okay, thank you for confirmation. So in that case, we shall start with solving another assignment. Okay, just hold a moment, please. Okay, everything working fine. Let me check once. Okay, so since you don't have any, since there is no questions to answer, so today we shall do solve assignment. One minute. So today we shall solve assignment 8. Okay. So hold on just. So today we shall solve assignment 8. Okay. So So first question is the following. So if you have any doubt, any question, without hesitation, you can unmute yourself and ask me. Okay, because this session are only for basically for problem solving, doubt clearing, this type of task. Okay. So the first question is that give example. The first question is that give example of a space which satisfies S3 having subspace which does not satisfy S3. That means you need to consider a space which satisfies the third separability axiom, but it has a subspace which does not have a third separable axiom. So basically, that means you need to provide a example, sorry, counter example which tells that subspace of a subspace of, so what is the third separable axiom? Third separable axiom is regularity, right? So you need to provide a example which tells that regularity does not is not inherited as a is not as an inherited subspace property. Okay, so try to consider such examples. That means you need to find some example space which is regular but having a subspace which is not regular. Basically, that's what you need to find. Okay, so think about it. Let me know. And by the way, what does regularity? So, of course, I'm not going to tell you the regular definition. So, anyway, the definition of regularity goes as follows. That means if you take any point, the definition of regularity is that, um, uh, okay. So, suppose if you take any, sorry, suppose if you take any closed set and a point, and if you take, then they are disjoint x naught, then we shall get an open set U containing F and V containing X naught such that U intersection V empty. Okay, such a thing is called a regular space. Now, if I construct example of a space which is regular but having a subspace which is not regular, okay, take your time, think about it. Let me know. It is not difficult. Just try to use the use. I mean, there are many space which you know as regular space. So try to use those. Okay, this should not be difficult. So try to consider such examples. Okay, it is not very difficult, I think. Think about it just. So, for example, so for example, what are the regulars? What are the spaces not regular? So, for example, sorry, for example, you can go. So, I mean, R suffix k, R with k topology. This is not regular, right? Just let me put it in the right side. So, R is solar, it is not regular. And we know about this, right? Uh, hmm. So now the question is, can you construct a space which contains R suffix k as a subspace, but this the bigger space is regular? Is it possible? Can you do something like that? Think about it. Can you think about any such space, Mustaq? It is not difficult anyway. Okay, so I'm giving you the example. So if we consider x is equal to a, b, c, d, okay, and you consider topology tau is equal to phi x d b d, sorry, b d c d b c d, and if we consider a to be b c d, then clearly our bigger a satisfies third third axiom, but a does not. Why? Because the subsets singleton b and singleton c of a cannot be separated. Okay, that is the argument. That means what? I mean, so basically this counter example. So x equal to a b c d, tau is equal to that given topology, and we are taking a to be b c d and x. So this tells that x is a second double space, but a is not. Now b and c of a cannot be separated, so that's what this tells. So this test, this basic test, I mean, this does not tell anything actually. So there's a counter example, but A is not separable axiom because singleton B, singleton C cannot be. These 2 points of A cannot be separated. Okay, so that is the argument. Okay, is that clear? Please let me know. Okay, so now go to the next problem. So the next problem tells that the next problem is So I have this out. This problem is clear. The next problem is as follows. The next problem is example of give example of a space X which satisfies a second separate axiom but not first. Okay, so try to consider count example like this. So basically the space which you considered yesterday, actually that space shall work. Okay, just you need to use a little bit trick to use that. I mean, you need to visualize that that should work. That is the point. Okay, there is really nothing to do. Think about it, let me know. So are you able to, even Mustaq, are you able to figure out that how this is happening, or any idea, any guess? One minute. Okay, so the example goes as follows. If we take x tau to be indiscrete topology, okay, and having at least two elements we're considering, okay, so this clearly tells that x is S2 but not S1. Okay, so that is the thing. There is literally nothing to do extra. So the example is what? 1 minute. So example which you are taking is that x comma tau to be indiscrete topology, order is greater than 2, and x is second countable but not x first countable. So an order of an x has at least two elements. So this space satisfies S2 but not S1. Okay. If you don't understand why, then try to explore definitions. There is nothing to explain, to be honest. Now question 3. Question 3 is what? So question 3 tells that So, so give example of a space X which satisfies S3 but not S2. Okay. Find an example of space X which satisfies S3 but not S2. Okay. Try to think about it and let me know. Okay. Sorry. Okay. So, so in that case, the example, so since Mustaq is not unable to give an example, so the example is as follows. Take x to be double done AB. Hold on a moment, please. Take x to be double done AB and tau to be empty set singleton A and X. Okay. Then X satisfies S3 but not S2. Okay. So why? Since the point A and singleton B cannot be separated. Give example of so basically if you take x equal to double done AB and tau was a given topology where they're taking the topology out with this, then x that is the third count will exist but not second action. So A and B cannot be separated. Okay, so that is the argument. Okay, so there is nothing more to explain. Okay, okay. So now 1 minute, everything will be fine or not? Okay. Shit. Now, so the next question is question of four. So basically, in this question we need to find an example of a space X which satisfies S3 but not S1. Okay. So you need to find an example of a space X which satisfies S3 but not S1. Okay. So try to think and try to figure out which which space shall work. Okay, so basically this example you can take as previous one, so there is no problem, you can consider the previous example also, but with a little twist in the topology. That's what you need to consider. Okay, else everything can be else the rest of the thing will be same actually. Okay, so yeah, try to figure this out, and it shall not be it should not shall not be difficult. Okay, take your time, let me know. Hmm. Okay. So, hmm. Hmm. So for this, what we can take x to be double done AB, tau to be phi AX, okay? Then clearly x satisfies S3 but not S1. Why? Since the points A and B cannot be separated. Okay, so that is the argument. Okay, so basically here what we are doing, 1 minute. So basically here what we are taking x to be double to AB and tau to be this, then x satisfies S3 and but not S1 due to the algorithm. The point is that the choosing the topology tau is the crucial for making this counter example. Okay, and rest the thing you already know. There is nothing to explain. Okay, so that is the thing. Okay, so now okay, so now um, okay, so this assignment this is so now we shall go to objective assignment 8. Okay, so let me open it. Okay, so 1 minute. Okay, so just hold a moment, please. Okay, okay. So previously we have left this subjective, objective assignment 7. Okay, so today we shall start from the assignment 7 only. Okay, okay. So okay, so this is Assignment 7, objective. Okay. So first question is the following. Okay, before going further, let me know, is there anything else? Okay. The first thing is that the first question is the following. So let F be a filter on X, then tau A union phi is a topology on X. Okay. So it is true or false? So basically, if a filter, then can we get the topology induced from the filter directly? Is it true or false? Think about it. Let me know. Take your time. So basically, you need to just explore the definition of filters. Nothing more than that. Okay. That is the thing all you need to do. Hmm. Okay. Working fine. Okay. Just hold a moment, please. Hmm. 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 But no. Sorry for the inconvenience. There is some serious software issue. So basically, you need to export definition and try to figure out this problem. Okay. And it should not be difficult as well. Mm, mm. Okay, so the argument goes as follows. See, it is true. Obviously, why? Because since x belongs to tau and this filter and the tau is closed under finite inter sorry under finite under finite intersection and arbitrary union. Okay, so of course, so it is closed. So that's why it forms a topology. Okay, that is so it is true only. Okay, now go to question number two. So the question number two is telling that uh, if f1 and f2, these two are filters on X, then if A intersection B, A belongs to f1 and B belongs to f2, is a filter on X. So basically what it is asking for, if you have two filters f1 f2, then is their intersection as a filter or not? That's what basically they're asking. Okay, so okay, see, first of all, this should be false. Why? Because if it is true, then you must have read this, right? I mean, if it is true, that is something interesting. That means what? If we have any filter, then we can get a sequence of shrinking filters. Okay, but such a thing is, I mean, we have not seen in the theory part. So possibly such a thing is already false. So try to provide a counter example for such a statement. Okay, take your time. Let me know. Think about it. Okay, take your time. I shall be back in a few moments. Hmm. Okay. So, so, Mustafa, are you able to figure this out, or whether it will be true or false? Let me know. So anyway, it will be false. Okay. How if we take AB belongs to X and if we choose F, sorry, we are taking X to be doubleton AB and F1 to be singleton A comma X and F2 to B comma X, then phi is equal to singleton A intersection singleton B that belongs to F1 intersection F2. But that shouldn't be the case, right? So directly we can say that such a statement is false. Okay, I hope this is clear. Okay, so now go to question number 3. So this question 3 tells that suppose X be set having at least 2 point, and if beta is a base for a filter F, then every element of F can be written as union of members of B. Okay. So what this so that student is what 1 minute. So that's telling that if X is a set having at least two elements, beta be a base for a filter F, then every element F of F can be written as union of members of beta. Okay. So that is the thing. Okay. So okay. So it is basically asking same that if a base then it opens that is union of in every opens that is a union base element. So the same thing is asking in analogous thing to the filter. So try to think and let me know whether it is true or false. The same argument you can say is that if it is true, then you must have read in the class notes or any books. But since you have not seen any such like that, so it is not true anyway. And it is not true, but you need to provide counter example for that. Okay, that is the thing. Think about it. Let me know. Hmm. Hmm. Okay. So, of course, such thing is not true. Okay. So the good counter example is as follows. Okay. 1 minute. Hmm. A counter example is as follows. Shit. Okay. So first of all, it's false. Okay. So we are choosing A B belongs to X and taking F to be singleton A X and beta to be A. Then this beta is a basis for F, but X cannot be written as union of members of B. Okay. So basically what we're getting is that we take F to be the singleton A comma X and beta to be singleton A, and then of course the basis of F cannot be written as the union of members of beta. Okay. So that is the thing. So I mean obviously there is nothing to explain more. This is the counter. This counter is what you can check by yourself. Okay. I'm not explaining this anymore. It is very easy, I guess. Okay. So now, hmm. So now the next question is as follows. Let X be a set having at least three elements and let A B belongs to X. Then the filter generated by the subspace, yes, X minus singleton A singleton B contains exactly four elements. So we are considering X. So we are considering X to a set having three elements are taking to, and then you're considering the filter generated by the subspace yes equal x. When it's B. So and contain the four elements. So yeah, try to solve it first. Okay, take your time. Let me know. Take your time. Let me know the answer. Okay. Hmm. Hmm. Okay, so hmm. Okay, just hold a moment, please. I missed. Okay, so now the next question is as follows. The question is that let X be a space and let F be a filter on X such a way that every cluster point is a limit point of F. Then F is a ultra filter. So yeah, so that is the argument. So I mean there is a statement. So basically it is saying that if X is space and A be a filter on X, every cluster point is a limit point of F, the F is ultra filter. Okay. Take your time, think about it, let me know. It is not, I mean, the point is that it is, anyway, it is false, but I'm just telling you it is false, that you need to provide a counter example which tells actually it is false indeed, okay? Take your time, let me know. Mm, mm. Okay, so the point is that that statement is false, okay? Why? Because if we take x equal to n and f is equal to the cofinite filter on x, then for any x belongs to x, we have nx is equal to x minus A union X, and A is finite. Now since Nx sum of F, so this tells that F converges to X and F converges to every point of X. Okay, but F is not an ultra filter on X since neither the set of neither the set of even numbers nor the set of odd is enough. If we co-finite filter on x and for any x belongs to nx is equal to, then this does f converges to and if converges to every point, just if converts every point of x, but f is not an ultra filter on x since neither the set nor the even numbers nor the set of odd is in f. Okay, so that is the thing. Okay, so please go through the argument once and let me know is it clear to you, else we can go for the next question. Okay, I will in a few minutes. So, okay, so okay, so I have this argument is clear. So now we shall go to the next question. The next question is telling that so we have some x comma tau a space which is non-discrete, not indiscrete. That means other than I mean there is non-trivial open set. Okay, that is a thing. Okay. Then question is then there exists a filter f on x such that every element of x is a cluster point of f and there exists a point in x which is not a limit point, a limit of f. Okay, so this is the whole question. The question reads as follows: x comma tau is indiscrete, then there exists a filter f on x so that every element of x is a cluster point. That is one. Second is that there exists a point in x which is not a limit point of f. Okay, try to figure this out. Okay, take your time, let me know. So first of all, it is true or false, think about it. Okay, for your sake of simplicity I am telling this answer, this is actually true. Okay, now try to figure out that why I mean basically you need to figure out some I mean sorry, I mean you need to argue because it is true, true only. So you need to argue that why it is true. Okay, take your time, let me know. Hmm. Okay. 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 So the argument goes as follows. So the argument goes as follows. The point is that if we take x equal to singleton x, then for all a belongs to U belongs to neighborhood of A, okay, but U doesn't belongs to F. Whereas U intersection U is equal to U non-empty. So that is the argument, okay. So yeah, so okay, so that's all for assignment sub objective 7. So now let me, okay, till now if you have any problem and doubt, please let me know. Okay, so 1 minute. Okay, so okay, so now let's go to assignment 6, objective question. We have already done the subjective part, so now let's go to the objective one. Okay, so where is my okay, now so mm, uh, okay, so now the question is the following. So if it is a true false question, first question is that if Ax metrizable non-discrete space, then X is second countable. If X is metrizable non-discrete space, X is second countable. So it is true or false? Think about it. Let me know. Hmm. So, any idea how to approach this problem? Okay, so okay, so the answer will be as follows. First of all, it is false. Okay, why? Because consider the disjoint union of because consider disjoint union of uncountably many. Consider disjoint union of uncountably many copies of her. Okay, so that's why it is false. That is, we are considering. Okay, I mean that is okay. So there is nothing to explain more. Okay, now question two. Second question. Sorry, second question is that the space R2 is perfectly normal. Is it true or false? Think about it. Take your time. Let me know. I shall within few minutes. Bengali Panput. Just hold a moment. Okay, so Mustaq, are you able to figure out why R2 is perfectly normal? I mean, the thing is, it is anyway true that I've told you already, but why it is perfectly normal? Okay, so the answer goes as follows. The point is that R2, not only R2, I mean, any metric space is perfectly normal. Okay, it is true always. Okay, so there is nothing more to explain. Any metrics are perfectly normal. Okay, that is the thing. So that's what is true. Okay, now question number three. So question number three is that on Z we are defining A less than equal to B if A minus B even. Okay, then less than equal to is a direction on Z. So okay, so is it true or false? So yeah. So Mustaq, think about it and let me know. The point is that this is only z, so it should not be difficult. I mean, just what is the direction? Direction means if you take any points a and b, you will get a c such that a less than or equal to c and b less than or equal to c also, right? So try to use that definition and try to exploit it. Okay, take your time. Let me know. Okay, so okay, so the point is that it is false. Why? Because if we take point 2 and 3, then we shall not get in c in z such that 2 less than equal to c and 3 less than equal to c. Of course. So there is a contradiction, okay? So there is nothing to explain, I guess. So basically, I mean, why if we get such a thing, this will tell what? 2 minus c even. If we get such a thing, this will tell what? 3 minus c even. So jointly it tells, sorry. So jointly it tells that um 1 even, which is of course not the case, right? So that's why, I mean, so that's what the thing. Okay. So yeah, I have this clear. So yeah, so take your time and let me know, or else we shall go to the next problem. So, okay. So now we shall go to the next question. The next question is just suppose we have a space X and S be a net in X, okay? And A subset of X such that S converges to a point in A. Then the thing is that S is eventually in A. Okay, so that is the thing. So S be a net in X and A subset of X such that S converges to a point. Then the thing is that S is eventually in A, okay? So take your time, let me know. So it is true or false. So basically, eventually it means after certain finite steps, rest of the portion shall lie inside A. I mean, few of the elements of S may not lie, but after certain instance, everything will shall lie into the S. Okay, so that is the thing. Hmm. Okay, so okay, let me find the next question. Wow. Okay, so the next question is as follows. Sorry, not. I mean, okay. So this is false. Firstly, okay. Why? Because if we take A to be any subset which is not open, then we have actually proved that there exists a net, yes, converging to a point in A but not eventually in A. Okay, so this thing we have already proved. So basically, that is the thing. So the point is that if A is any subset which is not open, then we have proved that there exists a net, yes, converging to point A, but not eventually in A. Okay, that is the argument. I mean, that is the thing. Okay. yeah, so that's why this argument is false. So now go to the next question. The next statement tells that, hold on a moment, please. Next statement tells that the intersection of two eventual subsets is eventual. So it is true or false. So yeah, so think about it and let me know. Okay. Okay. Now, so okay. So the solution is, first of all, it is true. Okay. How if we take E and F are eventual subsets of a discrete set D, then we'll always find to point AB belongs to D such that whenever A less than equal to X, X belongs to E, and whenever B less than equal to X, we'll always have X belongs to F. Okay. Okay. We'll always have X belongs to F. Now we are choosing C belongs to D such that A less than equal to C, B less than equal to C. Why? Because since D is directed. And now let X belongs to D such that C is less than equal to X. Okay. Then A less than equal to C, which implies that X belongs to E. And again, C less than equal to X, which implies that X belongs to F. And hence, X belongs to E intersection F. So that is the argument. So that is a full argument. That means what? Hmm. So AB belongs to D such that A less than equal to X and X less than B. So now C belongs to D such that A less than equal to C and B less than equal to C. The example X belongs to D such that C less than equal to X and A less than equal to X. So that's so this tells that X belongs to E intersection F. Okay. So that is the argument. Okay. So this is assignment 6. So let me know till now, do you have any question or doubt? So now, okay, okay. So now still you have 6 minutes left. So we can start with assignment 15 MCQ. Yeah, okay. So okay, so assignment you have done actually. I have just noticed, realized. Okay, so okay, so assignment 6 we have already done MCQ part. So I can't remember whether we have done assignment 2 MCQ or not. So let me check anyway. Okay, so let me check the MCQ. So now let's do MCQ of assignment 2. So there are since there are so there so we shall go okay so 3 4 minutes more. So the first question is as follows. Let F R3 to R be a C1 function and P x naught y naught z naught be such that f of x naught y naught z naught equal to 0. Now consider the following statement. The statements are there exists rho greater than 0 and a unique C1 map G from okay, forget about the assignment. So there is one question I must ask. So question is that if uh, X Hausdorff, if and only if this diagonal of X this thing is closed in x cross x. So the point is that such a thing is always true, and it is always useful to keep this type of thing in mind. Okay, x house drop if and only if this is closed in x cross x. Okay, so this is, I mean, just you can, yeah, I mean, this is a fact. You try to prove by yourself. Okay, you are not going to, we are not going, I am not going to prove that. It's a very easy thing. You can do this by yourself. Okay. Now the next question we can ask is that hmm, x to y, we have two map f and g, y house drop. Okay. Then consider the set those x belongs to x as an fx equal to gx. Show that this set is a closed set, closed in x. Point is that such a thing we have already, such a thing you must have done in case of real analysis, but for topology, this is bit for arbitrary topology is a bit difficult. Why is house draw? So basically, you need to use this fact here. Use it, okay? You can take your time and figure this out at home. Right now, I mean, there is no point of figuring out this right specifically right now, okay? You can take your time and think about it later on. It is not very difficult. It can be done easily, okay? So, okay. So, so that's all for today. We shall end here. So before, okay. So, does anybody have any question? So, okay. So Mustaq, do you have any question? Mustaq, do you have any question? Please let me know. Okay. So in that case, I'm leaving the session. Thank you. We shall meet on the next Friday.